Hi everyone, so today we are going to continue on with our matrix operations, specifically matrix multiplication. So to warm up, I want you to complete the bell ringer, just a little bit of practice with the operations we've already talked about, adding, subtracting, and scalar multiplication. So take a moment on your own to answer the following two questions. Now to check your answers. For the first one here, you should have gotten 0, 0 as your answer. It's a 2 by 1 matrix. And then your second matrix, after you subtracted and then distributed that negative scalar, you should have had these answers here. Okay. Now, again, we talked about addition, subtraction, and scalar multiplication. Today we're going to talk about the semi-lengthy process of what is matrix multiplication, talk about the different properties of our matrix operations, and also how we can do some stuff in our calculators. So if we look here, this is actually from the 34-1 lesson, and it was on page 488 in the Springboard textbook. And this is where we ended the other day. And something that we talked about was in order to find the number of strips we needed for specific things. For number 11, we had to take column 1 here of S and multiply by row 1 here, each of those entries together, and we would end up adding. And then we did kind of the same process here with the cherry and the row for Chandra. We would take those values, multiply them, and add them together to get those total numbers. What we were doing was actually matrix multiplication, kind of unbeknownst to us. So notice then page 489 then in the Springboard textbook, you kind of have those two entries already filled in, the 52 and the 24, and we need to also get the other values as well. So when we are finding, to kind of keep this process going, we need to kind of have this system down. So to get the maple for Monique, the number of strips of maple we need, we're looking for row 1, column 2. So what this is going to require us to do is take row 1 and column 2 of our two matrices that we are given, D times S, and again multiply each entry by its corresponding entry and then add the values together. So we would have 5 times 3 plus 3 times 5 plus 4 times 5. So 5 times 3, 3 times 5, 4 times 5, for a total then of 15 plus 15 plus 20, which would give us 50. Okay, and then I'm going to erase this so we can see a little bit better here. If we do the next piece then, if we want the cherry for Monique, we would take, again, this is row 1, column 3, so we would take row 1 and then column 3 here. Okay, so row 1 and column 3. So 5 times 2, entry 1 and entry 1, and plus 3 times 4, plus 4 times 0. So 10 plus 12 plus 0 is a total of 22. So hopefully you're starting to see a little bit of the pattern here. This next one, again, I'm going to erase here so we can keep it a little clear as you follow along. We're going to look for now the walnut strips for Chandra. So we want the row 1, column 2, row 2, column 1. So we're going to take row 2 times column 1. So 4 times 4, 4 times 0, and, oh gosh, that was very poorly written, and 2 times 8. So 16 plus 0 plus 16, we have a total of 32 here. And then last but not least, for row 2, column 2, what we need here now is row 2 times column 2. So it's going to be 4, 4, and 2, 4 times 3 plus 4 times 5 plus 2 times 5, for a total of 42. Okay, so notice as we look for the entry here in row 2, column 1, we needed row 2 times column 1. And when we wanted row 2, column 2, we needed row 2 times column 2 to find those values. Okay, so that's kind of that operation that they're trying to put in the picture there. Well, as we continue on with these values, okay, notice that if we are talking about the overall product matrix that we got, which row in matrix D was used to calculate the number of maple strips that Monique needed? Well, that's going to be when we used row 1. Okay, so when we used row 1, we needed that. And then we used column 2. It's the column in matrix S that we used to calculate the number of maple strips. So column 2 here that Monique needed to purchase. So column 2. Well, the notion then when we're talking about the entries in row 1, column 2 is this guy right here. Again, we talk about entries as row 1, column 2. So entry 1, 2. Kind of like we were talking about on the last page, kind of the rows and columns that you are using end up giving you that entry. So another example, if we were talking about row 2, so here's row 2, and in matrix S, we were talking about column 1. Well, row 2 and column 1 would be entry 2, 1, aka row 2, column 1 in the product matrix. Okay, so just to kind of talk about a little bit of this when we are getting situationally, if we're talking about D times S matrix, okay, using a row by column name, well, here's that product, D times S. It is the person by the types of wood are what that matrix is representing. So the rows are denoting which person we're talking about. The columns then are talking about the types of wood. Well, what category of information that was common in D and S is now missing from that product? Well, our styles. Notice both of these had the styles in common, but in the product, we got rid of that. So notice that that overlapping piece that they had in common was kind of combined, and we did it into just the total number of styles there. And then last but not least, what information is given by the entry in the first row and the third column? Well, first row, third column is the number of strips of cherry wood that Chandra needs. So that's going to be denoted by entry 1, 3, so row 1, column 3, and again the number of cherry strips she would need. And last but not least, what would the entry in the second row and the second column, so second row, second column, denote? That's going to be the number of strips of maple wood that Chandra is going to need. And again, we're going to denote that by 2, 2, row 2, column 2 for that. Now, as we move on then to talking a little bit more about this, another pattern you are probably starting to see is that in order for this matrix multiplication to happen, we need to have something in common. So we had matrix D times matrix X, matrix D, matrix S. And this was a 2 by 3 matrix. This was a 3 by 3 matrix. So notice here, those style matrix that we talked about in common, they matched, okay? And then our overall product was a 2 by 3 matrix. So in order for matrix operations to occur, the number of columns in the first matrix, let's put an N here, in the first factor has to equal the number of rows in the second factor. So notice those 3's had to match in order for this to occur, okay? And then the resulting size was a 2 by 3 matrix, 2 rows, 3 columns. So if we have R, S, and T here and their sizes, we want to list all the possible products that we could have for R times S and S times T and T times R, basically, because we need to see which ones are going to actually be possible. So for instance, R is a 3 by 2 matrix. S is a 2 by 4 matrix. These match, so this is possible. And its result is going to be a 3 by 4 matrix, this piece here. Another possibility that's going to work out is S times T, because they're telling us S is a 2 by 4 matrix, T is a 4 by 3 matrix. These inner pieces match. The outer pieces then will tell us how big our product matrix will be. It's going to be a 2 by 3. The last possibility that is going to be able to work is T times R, because if we have it in this particular order, these inner pieces match and then these outer pieces match, right? The number of columns in the first factor matches the number of rows in the second. So those check out, and our resulting product then is going to be a 4 by 2 matrix. Okay? If we try to go in the reverse order, notice here, it's not going to work out because the columns and the rows don't match. So this is not possible. Okay? Now, moving on from there, if M and N are the dimensions of matrix L, and matrix T is N times P, what has to be the dimensions of the product? Well, notice here, the inner dimensions match, so this is going to be possible, and our product is going to be an M by P matrix, whatever size that is. And again, we know for this to happen that N has to equal the number of columns, N has to equal the number of rows in T. Okay. Now, from here then, so we know again the inner dimensions have to match and the outer dimensions tell you the product size. So just to kind of summarize that. Okay. And now I want you to look at the check your understanding section. Okay, we are going to find each matrix product. So before we start, which of these 3 is not going to be possible? Well, hopefully you noticed here that B is going to be our problem that is not possible, because this is a 2 by 3 matrix. This is a 2 by 3 matrix. The 3 here and the 2 here do not match. So this one is not possible. Okay, so that's going to save us a little bit of work from the beginning. A and C are possible though, because this is a 2 by 2 and this is a 2 by 2, so your inner dimensions match here. And then this is a 2 by 2, this is a 2 by 3, inner dimensions also match here, so they will work out. Now our resulting products here, this one is going to be a 2 by 2 because of these outer pieces. This is telling us it is a 2 by 2. And this last one is going to be a 2 by 3 because, again, of the way the outer dimensions line up. Now, to get each spot, so if we look here for entry 1, 1, we need to take row 1 times column 1 to get those values, multiply and add. So 4 times 3 is 12, plus -1 times 5 is -5. 12 minus 5 is 7. Well, to get this next piece, erase here. To get our next piece, we now want row 1, column 2. So again, we're going to take row 1, but multiply it by column 2. So 4 times negative 2 is negative 8. And then negative 1 times 1 is negative 1. Negative 8 minus 1 is negative 9. Last but not least, if we are looking for the second row, we need to use the second row here. And for column 1, this first spot here, we'll use column 1 of our second. So negative 2 times 3 is negative 6. 6 times 5 is positive 30. So negative 6 plus 30 is 24. And last but not least, row 2, column 2 involves us using row 2 and column 2. Negative 2 times negative 2 is positive 4. 6 times 1 is positive 6. 4 plus 6 is 10. Okay. Now, when we do this same process for the second one, okay, you should check your answer here. Pause the video, but then check your answer in a moment. You should have had 2, 4, negative 16, 44, 8, and 8. Your final answers. And last but not least, if we know that H is an M by N matrix and G is a P times Q, P by Q matrix, what restrictions would have to be placed on this in order for this multiplication to happen, H times G? Well, we know that N would have to equal whatever P is in order for this to work. All right, now the time has come to start talking a little bit more about using our calculators and some properties with addition and multiplication. So if we were to add these two together, okay, adding A plus B, well, we know from the other day that we can add these two together because they're the exact same size, and we would just add up the corresponding elements. We'd have 9, 8, 7, and 2. And this answer is actually going to be the exact same if we flip those around and add B plus A. We're going to get those same entry values. Now, the same cannot necessarily be said for A times B and B times A. Now, this is where you're going to get your calculator involved to start checking your multiplication answers. So, in order to type a matrix into your calculator, you're going to hit second and then X to the negative first, and you're going to get into the matrix menu. And what you're going to do is you're going to scroll over to the edit option, and we're going to type in matrix A. Now, matrix A is a 2 by 2 matrix, and the elements are 4, 2, 5, and negative 2. Now we're going to do the same procedures. Second matrix, we're going to edit now, scroll over matrix B, also a 2 by 2. And we're going to type in 5, 6, 2, and 4, the elements there. And then we're going to hit second mode to quit out. Okay, we edited those two into the calculator. Now, if we multiply these two, instead of doing this by hand, we're going to go back under the matrix menu. We're going to select option 1, and we're going to multiply that by second matrix. We've edited in. And you're going to see far quicker than we would have been able to do this by hand that our value for A times B is a 2 by 2 matrix, 24, 32, 21, and 22. B times A, on the other hand, is not necessarily going to be that. So again, second matrix, this time B times matrix A. Notice, slightly different of an answer, right? We have 50, negative 2, 28, and negative 4. Now, normally with addition and subtraction, addition and multiplication, the order is not going to matter. Whether we do a plus b, it's equal to b plus a. A times b is equal to b times a. That's known as the commutative property. Okay, and you'll see that on the side. That's the commutative property. When this comes to matrix addition and subtraction, do these properties hold? Yes, for addition. Order does not matter. We could do a plus b or b plus a. We get the same answer. But it's not going to be the same for multiplication, and that's shown by our counterexample up above. And not always going to work out, so we can't assume. So now notice here for our last couple examples here, right? We have B and C, and then 3x3 matrices D and E. And to save us some time, I already have these calculated, but if we take our calculators, and feel free to practice with your calculators so you can get used to typing these in. If we type in B, C, D, and E, and notice we already have B in the calculator, so you would just have to edit C, D, and E. These would be 3x3 for your dimensions. B times C and C times B both equal the same matrix value, okay, same product. Same idea with D times E or E times D. They end up being the same product, and they also happen to be the exact same as what matrix D was. Well, these two matrices, C and E, are the reason that that is working out for us, okay? These are known as identity matrices. And for a square matrix, we can have an identity matrix where we basically have the same number of rows and columns, and the diagonals are all going to have an entry of 1. Everything else is a 0. Okay, so again, these only occur in our square matrices. So again, where the rows and the columns are the same value. Okay, and diagonals all 1, all other entries are 0. Okay, and when you multiply something by an identity matrix, again, this is only for square matrices, you're going to get the same answer either way you multiply, and it'll be the same as the non-identity matrix. Okay, now almost done here. 12 and 13 are the last two examples we're going to talk about. We have A and B, where we have A plus B is going to give us the sum 2, 9, 3, 5. If possible, what would the value of B plus A be? Well, we know that the answer of B plus A is going to be the exact same thing that A plus B was, because addition is commutative. Now, on the other hand, for 13, if we try to do B times A, that's not possible at the moment for us to figure out what the matrix is going to be, because we don't know what matrix B or matrix A are. We don't know if it's possible. We definitely, even if it is possible, don't know what the matrix is going to be, because it's not necessarily the same answer. Okay, so that's where it's going on there. Again, we don't have commutative property holding for matrix multiplication like it is for addition, right? Not commutative. All right, now the practice for this lesson, I do page 493, numbers 15 through 23. Don't worry about 24 at the bottom. Thanks, everyone.